Engineering Mechanics Statics Lecture 11. The present lecture will explain the subject 2, which is equivalent system, and we're gonna go this part: the basic principle, resultant of a force and couple system, and further reduction of force and couple system. This is the objective. First is to determine the effect of moving a force, and second is find an equivalent force couple system for a system of force and couple. Okay, now let's revise about force and moment system. Before this, we learned about the chapter 2 is all about particle of the system. So the force and moment system is, we can see typically like this. Okay, so let's say there's a point here and we denote as A, and the point is subjected to the multiple forces like FB, FC, FD, and the weight. So the point A here, we call it as a particle. Okay, a particle A, because it is in the form of point. The point is subjected to the force. Okay, so to find the resultant force, simply F resultant is equal to the total force of all the force, FB plus FC, plus FD and weight. Okay, this is for particle, which is we learned previously in chapter 2. Okay, but for now in chapter 3 we learn about body, not particle or point, but body. So the point here is replaced with one body like this. Okay, so this body is subjected to the multiple force, just like this one, but for this one is object or body, or we call it as a rigid body. Okay, so how we want to analyze if the force and moment is subjected to a body like this. If it is a point, we simply can do the analysis because it's just only one point. But how about the body? Because body is one body, big one body like this. Okay, so we can do the equivalent system. We can make this system equivalent to this one. Okay, so it is like the external force exerted on the body is also act internally. The effect of the external force is internally the same. Okay, like this one. Okay, so we can move the subjective force in the surface body into the internal of the body, or we can simply put in the center of the axis origin. Okay, so like this. It seems that also there is a point here. It's become a particle analysis. Okay, so external force give the same effects internally on this body. Okay, now let's look at some other examples. How we represent the force and moment system with the equivalent system for rigid body, in case for 2-dimensional and 3-dimensional model. Okay, let's look at first for 2-dimensional example. Okay, if you hold a ruler like this, so this ruler is your rigid body, and then exerted force in this region. So actually you will feel the effect of the force at your hand, right? Okay, so we can represent this model which to the equivalent model like this. So the force is also actually have the effect at this point. Okay. Same goes to the moment cases. Okay. If there is a force perpendicular to the line of action, if you still remember, to produce a moment, the line of action must be perpendicular with the force. So it will produce a tendency to rotate. Okay. So the effect of rotation and the force you will also feel in your hand holding here. Okay. Or the source of the rigid body where it started. Okay. In this case from here. So you will feel the force and the moment at your hand also. So we can represent this model with the equivalent model like this. Okay, so there is a force here. You feel the force here. The force is here, but you feel the force. You also feel the force here, and the rotation here. You can also feel the effect of rotation in your hand. Okay. How about the 3D example? 3D example is same thing like 2D. Okay. If we have a force here in the same axis with the z-axis, so this external force, the effect will be feel in the source of where the rigid body started. In this case, in the origin. Okay, so the external force here, the effect will be the same internally here. Okay. Same goes for the moment cases. If there is a force not other than in the axis x, y, or z, maybe outside of those axes, so the moment will be created because there is a line of action r here, and so any force on the axis, maybe x, y, z, it will not produce a moment. But if let's say it is on the x-axis, but there's a line of action here, sorry, an option D here, so your force is over here. Okay, so this way the moment will be produced, but when it is on the axis, whether x, y, or z, it will not produce a moment other than the axis location, like this one or this one. The moment will be produced. Okay. So the effect of external force here also have the effect internally here. So we can replace this model with the equivalent model. So we move the F here into here. Okay. Because the effect of force in the external part also feel in the internally part. Okay. So the moment here, the rotation is in this direction. Sorry, the moment was in this direction. Okay. So the whole body will rotate, will have a tendency to rotate, but we can replace it within the body. Okay. So here. So when you represent this rotation with your right hand rule, it will show that the direction of moment was in this way in your thumb. So here you can put the moment also from the origin here this way. Okay. This is your moment, so this is your F. So for summary, if you have a rigid body here like this, apply with the force over here, and there is a line of action from the fixed position or from the origin. Okay, so the moment will be created or produced. So you can represent this model into this model. So you can put the F external here into the internal position here. Okay, so because the rotation is like this, so the moment will be this way, or this way somewhere here. So you can use your right hand rule. So this direction of moment you can put from here, okay, internally from here, okay, just like that. Okay, so next is the one that we discussed just now is for one force only. So for now it has more than one force, which in this case is two force, F1 and F2, or it could be more than, it could be multiple forces, 1, 2, 3 or 4 forces. Okay, so for more than one forces, the process is the same, so you can represent this model. The force here is attached externally, okay, so you can represent with the equivalent model where the force can be put internally here in a fixed position here, okay, in fixed position here, and then or internally in the source of the rigid body where it started. Okay, so for the moment also you can put the direction of moment starting from the point here also. Okay, okay, if your force here and here and your line of action here and here, so this will produce a moment, let's say in this direction, okay, this direction, so this one in this direction, okay, so using your right hand rule here, this is your right hand rule, so this is significantly your moment will be in this direction, okay, same to this one, so in this direction. So this model simply become like this one, okay. So we can further simplify this model become this model, okay, where you can replace these two force to become only one force, which is resultant force. To get the resultant force, you simply just sum up these two forces, okay, using this formula, okay, and then same goes to the moment. These two moments you sum up to become one moment, which is m resultant force, okay. So these two you can replace with these forces, this single moment, which is m resultant, okay. The formula is also same like this. Okay, same goes to the two-dimensional cases. If you are holding a ruler like this, instead of one force, there is a two force. Okay, so the first force, there is a line of action here, and the second force, the line of action is 2D. So these two will produce a moment, and a force. So you can replace these two force and moment become single force and single moment. Okay, so which is F resultant and moment resultant. F resultant is F1 plus F2, and resultant is this one. Okay, so you can feel the total effect of force and moment in your hand. Okay, so we can represent this model become this model. Okay, the external force here also act, also the effect also act internally here, okay, in your hand from the source of the rigid body started. Okay, let's go back here. We already discussed about multiple forces for 3D. Okay, so if let's say there is a multiple force here, okay, so you can simplify this model into equilibrium model, become like this one. Okay, so you can represent this external force and the moment become like this one. So the force is acting internally, and the moment also. Okay, so you can actually further simplify this model. Okay, if the force and the moment is in a position of 90 degree or perpendicular position between those elements. Okay, so you can eliminate this moment, okay, by moving away the force here into the distance of d. Okay, because d is equals to mr divide mr m resultant over force resultant. So when you move the force a few distance here, a few meter here, so you can eliminate the moment. Okay, so it's actually like you reverse back from here to here. Okay, to here. Okay, so you eliminate the moment. Okay, so become this one. But for this time, this is for resultant force. Okay, for resultant force and resultant moment. So it's become like this. From this resultant force and moment, you eliminate the moment and become like this one. Okay, okay, so you can represent this this model with your right hand rule like this. Okay, so this is your force resultant and this is your d. So the force and the line of action here produce the rotation in this way. So based on your right hand rule, when the rotation is this way, so your moment will be in this way. Follow your thumb's direction. Okay, okay, simply is the basic concept of the force and the moment, but it must be perpendicular to each other between force and the moment. Okay, that's all.